Okay, good morning. So today I will give you a lecture on evidential clustering, which is basically the application of belief functions to clustering. Okay, so I guess most of you know what clustering is about. It's a part of machine learning, you can say. And its objective is to discover groups in data. So we have a data set, which may be a set of feature or attribute vectors. Okay, we say that this is attribute data. Or sometimes we only have dissimilarities between the data. So we have a matrix of dissimilarities. Dissimilarity, it means basically the same thing as distance, okay? Except that we don't require so many axioms to be a distance. So sometimes the data are like that, and we say we have proximity data or dissimilarity data. So the first goal is to discover groups in the data. And the second goal can be to assess the uncertainty in the group assignments. Okay, how much certain can we be of these groups? Okay. And for example, here we have an object. So here we have data set with two attributes. And okay, we have a partition in three groups. But for example, for this object, we may be uncertain whether it belongs to any of these two groups. And this one we can also be uncertain whether it belongs to any of the three groups. Okay, so this is an outlier. So we want to quantify this kind of uncertainty. So here I make the assumption that each object belongs to one and only one cluster. Okay. Consequently, we search for a partition of the set of objects. So what is a partition? It is a family of subsets, okay, of O, which are pairwise disjoint, and the union should be equal to O. So for instance, here we have a set of objects. Okay. The partition is to define some groups like this. For example, here I have a partition into three groups. The groups are pairwise disjoint. Okay, they don't intersect, and their union is a whole set. Okay, this is a partition. So what will be our frame of discernment? Okay, the frame of discernment is a space of solution, okay, to the problem. Okay, so it is basically a set of partitions. Okay, so either we fix the number of clusters, and so the frame will be the set of all partitions of the set of objects into exactly C clusters, and C is fixed, I denote it like this, or we consider the set of all partitions into at most C clusters, okay, or the set of all partitions of the objects, okay, whatever the number of clusters. Okay. So there is some unknown partition, okay, we don't know what it is, so the frame of discernment is a set of partitions, okay, and we can restrict the number of clusters or not. The problem is that these sets are very big, and we can even say huge. For instance, if we fix the number of clusters or groups, the number of partitions of n objects into C clusters is given by this formula. And here I plot, okay, so here this is a log scale. I plot the number of partitions into three groups as a function of the number of objects. Okay. So you see that with, for example, 200 objects, we have almost 10 to the 100 partitions. So this is really huge. It is estimated that the number of atoms in the whole universe is of the order of 10 to the 80. And 200 is not a big data set. So now the total number of partitions of n objects is called the Bell number, B sub n, and it is, of course, we have to sum the previous numbers for C equal 1 to n, because if you have n objects, you can have between one group and n groups, okay? And now it's even larger, but now we are very big already. So for example, for 200 objects, now we have 10 to the 230, something like that. partitions of 200 objects. And we usually handle data sets of thousands or tens of thousands of, and now in some applications, millions of objects. Okay. So this is really a huge set. So you will still read here and there in the literature that we cannot apply a Dempster-Shafer theory to large spaces, okay, because it has exponential complexity to combine the mass functions by Dempster's rule and so on. And yet, I will show that actually we can implement evidential reasoning with belief functions in such sets. Right? But you may have different objectives. Okay, maybe your objective has to be carefully defined. We may want to compute the degree of belief or the degree of plausibility of any subset of partitions. Okay, but this can be very difficult. And we define a set of partitions. What is the degree of belief of that? It can be very difficult to do that. But we can only be content to compute the plausibility of any single partition. Okay, and this is still difficult because there is a degree of conflict. Okay, but weaker goal is to just compute the plausibility of any partition up to some constant. Okay, and this we can do. I showed it yesterday that we can just multiply the contour functions. Okay, and if we drop the constant, it's very easy. Okay, and this allows us to, particularly, to find the most plausible partition. So here in the next slides, I will describe two ways to define belief functions on sets of partition. Okay, so of course we are not going to define, because you see, if the frame has 10 to the 100 elements, the number of subsets is 2 to the 10 to the 100, so it's absolutely enormous. Okay, we are not going to give mass functions with mass to each of these focal sets. So we try to find some simple ways to define meaningful belief functions on that set. Okay, the first approach is to consider pairwise belief functions, and it's quite similar to what I explained yesterday about matching relations. Okay, yesterday I showed that we have two sets, and we could construct belief functions on the set of matching relations. Okay, so here is a similar thing, but now the relations are equivalence relations, because a partition can be described by an equivalence relation. If two objects are in the same group or not, this is an equivalence relation. Okay, and then we will compute the orthogonal sum of simple pairwise belief functions in that set. So here the focus on pairs of objects. This is why I call these pairwise mass functions. So for any pair ij, I define theta ij with a set of two elements, where Sij means that object I and j belong to the same group, and not Sij means that these two objects do not belong to the same group. Okay, so you see this is quite similar to what I presented yesterday. And so we can define a pairwise mass function in that frame theta ij. It has a general form. We put some mass on Sij, some mass beta ij on not Sij, and some mass on theta ij. And now we are going to extend these mass functions to the set P of all partitions. Okay, pretty much as I did yesterday for similar but distinct problem. Okay, so this is theta ij. This is a set P of all partitions. Here, Pij is the set of partitions in which objects I and j are in the same group. Okay, so to say that objects I and to say that Sij is true means objects I and j are in the same group. It is the same as to say that the partition, the unknown partition, is such that these two objects are in the same group. Okay, so we have this refining mapping from theta ij to subsets of P. So Sij corresponds to Pij, the set of partitions in which objects I and j are together, and not Sij corresponds to the complement of Pij. So we will do this vacuous extension operation that we have seen yesterday. So the mass assigned to Sij is transferred to Pij, this set of partitions. The mass on not Sij is transferred to the complement, and the mass on theta, should be Ij here, is transferred to the whole set P. Now we have as many of these pairwise mass functions as pairs of objects, which is n times n minus 1 over 2, and we can combine them by Dempster's rule. Okay, but here again, as we did yesterday, we are only going to combine the contour function. Okay, so we'll only get the plausibility of any single partition. So first we express the contour function of Mij. So here the superscript P, it means that it is, I consider that it is a mass function on P. And so it is the mass on Pij plus the mass on P if P belongs to Pij. Otherwise, it is equal to the mass on the complement of Pij plus the mass on P, okay? Because the plausibility of the element is the sum of the mass given to all the focal sets that contain that element, okay? So this is a set of all partitions, okay? Here this is Pij, here this is Pij bar, okay? See, if I consider, so we have some mass on Pij, which is alpha ij. We have some mass on the Pij bar, which is beta ij. Okay? And the mass on P is 1 minus alpha ij minus beta ij. So if P is in Pij, the sum of the masses is alpha ij plus 1 minus alpha ij minus beta ij, which is 1 minus beta ij. And if P is now in complement, we have to sum the mass given to Pij bar, which is beta ij, and the mass of P, and this is 1 minus alpha ij. So we can write this compactly as 1 minus beta ij to the Pij times 1 minus alpha ij to the 1 minus Pij, where Pij equals 1 if P belongs to Pij, and 0 otherwise. Here, this notation with a capital I here is the indicator function. Okay, so this means this is equal to 1 if the proposition inside the parenthesis is true, and it is equal to 0 otherwise. So we have seen yesterday that the control function of the orthogonal sum is a product of the control functions, okay, multiplied by some constant that will not compute. Okay, so it's simply proportional for any partition P. Its plausibility is proportional to this. Right? To just take the product of these terms for all pairs of objects I and J. Okay, so here. Okay, so here I forgot to mention something, that because we use Dempster's rule, we consider. So we do the calculation as if the mass function Mij were distinct or independent. Okay, although actually it's not the case, because if you have 3 objects, if you believe, for example, I, J, K, if you believe that I and J are in the same group, and J and K in the same group, it constrains your belief that I and K are in the same group. Okay, so there are these transitivity constraints. Okay, but we forget about this. Okay, so this is okay. This is, but anyway, this can be just seen as a way to define the belief function. Okay, so
approximation, like an approximation.
It's a belief. Yeah, we can see this as an approximation. It's a way to define a belief function indexed by these parameters alpha ij and beta ij. Okay, and now so, finding the most plausible partition is just the same as maximizing this function, which I just take the log, okay, of this plausibility. subject to the transitivity constraints. Okay, so this would be a PIK here. I did a copy and paste because actually this is very similar to what we have seen yesterday. Here that should be the PIK, and this is a binary linear programming problem. Okay, so it can be handled by some software of linear programming. However, in practice, this problem can be solved exactly only for small n, let's say a few dozen, maybe with a big computer, a few hundred. But for large data set, we will need a special heuristic algorithm that maximizes this, and we'll see that later when I describe algorithms, okay, for evidential clustering. Okay, the second approach to define belief functions on sets of partition is through Credal partitions. So let O be a set of n objects, omega a set of groups or clusters. A Credal partition, sometimes I say the equivalent is, synonym is evidential partition. A Credal partition of O is an n-tuple of mass functions M1 to Mn, where each mass function Mi on omega is each Mi is a mass function on omega describing the uncertain membership of object I to one of the C clusters. Okay. So I will show an example in the next slides. First two remarks. The mass function here may be unnormalized. Okay. So in some algorithms, some of the algorithms I will introduce later, we allow some mass to be assigned to the empty set. And the mass assigned to the empty set will be interpreted as the degree of belief that the object does not belong to any of the clusters. Okay, so it will be useful to detect the outliers. And we can also remark that if all mass functions are certain, that is to say they have only one focal set, which is a singleton, then a Credal partition is equivalent to a hard partition. Okay, sometimes we say a hard partition to distinguish from fuzzy partition, Credal partition. Okay, so this is really a generalization of the notion of partition. So here is a toy data set with 12 objects. Assume that we have two groups, and here we see the masses for some of the objects. For instance, we see that object 3 here surely belongs to cluster 1. Okay, so we have a mass, M3 assigns a mass 1 to omega 1 and 0 to the other subsets of omega. Omega here has two elements, omega 1, omega 2. Object 5, okay, is seems to belong to cluster 1, but it's not sure. Maybe it's in the middle, so we can have some mass on 0.5 of omega 1 and some mass on omega 1, omega 2. Okay, so it means that we believe it belongs to cluster 1, but we're not 100% sure. Object 6 is right in the middle, so there is no way, we don't know if it belongs to cluster 1 or cluster 2. So for object 6, the mass, the whole mass will be assigned to the frame, omega 1, omega 2. And object 12 does not seem to belong to any of the two groups. So we have a large mass assigned to the empty set. Okay, so this is an example of a Credal partition. So here we can remark that this has some relationships with some other models of clustering. You know, there is fuzzy clustering. So in fuzzy clustering, each object has a degree of membership, UIK, to each cluster K, with a constraint that for each object, the sum of the degrees of membership to the different clusters is 1. Okay? So an object may belong 0.03 to this cluster, 0.05 to another cluster, and 0.2 to a third cluster, for example. So actually, if you have a Credal partition where all mass functions are Bayesian, okay, then this is, you see that this is the same thing as defining a fuzzy partition, because you can identify the degree of membership of object I to class K to the mass Mi of omega K. Okay, so a fuzzy partition is recovered in the special case where all the mass functions in the Credal partition are Bayesian. Also, if you have an arbitrary Credal partition, okay, sometimes it contains a lot of information. Okay, so when you want to explain the result to the user, it is useful to summarize the Credal partition. So a Credal partition can be summarized as a fuzzy partition by transforming each mass function into a probability distribution. Using, for instance, the plausibility transformation that Prakash mentioned yesterday. You just take the plausibility of the singletons and you renormalize, you get a probability distribution. Okay? So if you do this for all the mass functions, you summarize the Credal partition into a fuzzy partition, into something which is simpler. You can summarize further by just retaining for each object the most plausible class, for example, and then you get a hard partition. Okay, there is also some approach to clustering called rough clustering. Okay, so in rough clustering, each cluster is characterized by two subsets of objects, a lower approximation and an upper approximation. Okay, and essentially each object belongs to at most one lower approximation. So I will show you an example here. Okay, for example, I have some objects here. And rough, if you use some rough clustering algorithm, I might get some inner or lower approximation, for example, like this. So this is, we can call it the inner lower approximation of cluster 1. Okay, and this is the lower approximation of cluster 2. So this is a set of objects that surely belong to each of the clusters. Okay. And of course, each object cannot surely belong to two clusters. Okay, so these cannot intersect. Okay, and then you have the upper approximation, which are sets of objects that possibly belong to the cluster. Okay, so it contains the previous one, and so you might have something like this. Okay, this might be the upper approximation of cluster 1, and this might be the upper approximation of cluster 2. And here, some objects may belong to either cluster 1 or cluster 2. And so actually, the upper approximation defines a covering. Covering is a set of subsets, but that may intersect. Okay? But the union is a whole set of objects. Okay, so this is rough clustering. And actually, given a Credal partition, if all mass functions are logical, remember that a logical mass function is a mass function with only one focal set. Okay, so there's only a set component. There's no probability component. Okay, and then actually n defines a rough. Here's another mistake. Defines a rough partition with lower and upper approximations defined like this. The lower approximation of cluster K is a set of objects whose label is exactly omega K. Okay, so they surely belong to cluster K. And the upper approximation of cluster K is a set of objects whose label contains omega K. Okay, so it's just an object that may contain to cluster K. And we can get the membership values to the lower and upper approximations by the belief and the plausibility of any singleton. Okay. So here again, you see that the concept of rough clustering is a special case of that Credal partition. So it's a very general model of clustering. And also you can summarize, and I will do it many times because when you draw what you want to show in a graph, the result of the clustering, it's very convenient to show these lower and upper approximations. Okay, it's very easy to visualize and to understand. So given an arbitrary Credal partition, we can summarize it as a rough partition by approximating each mass function mi by a logical mass function. So there are different ways to do that. For example, you can just keep the focal set has the largest mass, okay, for each object. And so for each object, you have a mass function mi. You just keep the focal set with the largest mass. Okay. So it's like approximating the mass function by a logical mass function. And so it's like summarizing the Credal partition by a rough partition. Okay. So sometimes I will show you some results of clustering with two sets for each cluster. The lower upper approximation, they are computed like this, by this approach. Okay, so now here I will show that actually if you define a Credal partition, okay, so you give a mass function for each object, actually this is also a way of specifying a mass function on the set of partitions with at most C clusters. So the first step is to extend each mass function mi to the set, I call it F, curly F, the set of mappings from the set of objects to omega. I call these labeling functions. Okay. So for instance, here I have, let's say, 5 objects, and assume that omega has 2 elements, omega 1, omega 2. Okay, and so I can say that this object belongs to cluster 1. Okay, this object also belongs to cluster 1. This object belongs to cluster 2. This one belongs to 2. This one belongs to cluster 3. Okay, so this is a function f. Okay, and I call it a labeling function. Okay, it gives a cluster label to each object. So it is not the same as a partition, because if I just change the, if I just permute omega 1 and omega 2, I have the same partition, but a different function. Okay, this labeling function depends on how I label the clusters. Okay, this is if there are 2 clusters, it is arbitrary to say this one is cluster 1, this one is cluster 2, or this one is cluster 2 and cluster 1. Okay, we have to handle this. Okay, so I do, this is why here I do it in 2 steps. So each mass function mi can be extended to f as follows. The mass assigned to subset A of omega by mi is transferred to the set of labeling functions such that the image of OI belongs to A. For instance, here I will assume that we have 3 clusters, for example, so I will change a little bit my function. So for example, if I have some mass for object I, okay, assume this is object I, and some for object I m of omega 1, omega 2 is 0.5, for example. Okay, so it means that the image of OI is either omega 1 or omega 2. Okay, so there are 2, so I can consider the set of labeling functions such that the image of OI is either omega 1 or omega 2. Okay. So in general, for any subset A of omega, I can transfer the mass mi of OI to the set of labeling functions such that the image of OI belongs to some subset A. So I can do this for all the functions mi of the Credal partition, and I get the same number of mass functions, but this time defined on F, the set of labeling relation. then here I will make the assumption that the mass functions M1 to Mn are independent. And here it's more plausible than in the previous case, because here you can make judgment of what is a cluster, or the cluster for object 1, for object 2, and so on. We can, makes more sense because there's no logical constraints between these mass functions, so we can treat them as, we can assume that they are independent.
The first case, even if there is double counting, when you double count it, things that are plausible become more plausible. So as long as you're interested in the most plausible, there's no problem.
Yeah. Yeah. So assuming that these n mass functions are independent, we can combine them by Dempster's rule. And so the focal sets of the orthogonal sum are of this form. We take if A1 to AN are focal sets of M1 to Mn, and we do this for every way to choose a focal set for M1, focal set for M2, and so on, we assign the product of the masses of the intersection, okay? So the intersection here of these sets is a set of matching relations such that the image of O1 belongs to A1, the image of O2 belongs to A2, up to the image of ON belongs to AN, okay? So here we have the mass function on, we can compute, even though it can be expensive to compute it, but we can very well compute the corresponding mass function on the set F of labeling functions. So now there is a mapping, okay, for each labeling function corresponds to a partition in at most C clusters, okay? For instance, this labeling function here, okay, corresponds to a partition where these two objects are in the same group because they are assigned cluster 1. This one is alone in this group, and these two are in a third group. Okay, so you see that given labeling function, we can define the partition. Okay, so I denote by capital Phi the mapping from the set of labeling functions to the set of partitions, but this mapping is many to one because there are several labeling functions that correspond to the same partition. For instance, here, if I rename the clusters, and this becomes omega 3, omega 2, for example, and omega 1. So now I have a different mapping because now the image of this one is omega 1, okay? But the cluster is the same. So actually, you see that this set of partitions, P sub C, is a coarsening of F, okay? Because each partition corresponds to a subset, okay, of labeling functions. So I define the restriction. So I denote like this: M superscript P sub C. So superscript is always the frame, okay? When mass functions with different frames, I use this superscript notation. So M superscript P sub C is a restriction of M superscript F in P sub C, and it is obtained by transferring each mass given to a set of labeling relation to the set of partitions represented by a labeling relation in F. So we assign the mass given to a set capital F of labeling relation, we transfer it to phi of F, which phi of F, the image of big F, is a union of phi of small f, or the image of matching of labeling functions, small f, in F. So I just shown that a Credal partition can be seen as a compact representation of a mass function on the set of all partitions with at most C clusters. So here I work out a complete example. So I have 3 objects, 2 clusters, and we have this Credal partition, and we have mass functions M1, M2, M3. Okay, so we believe that object 1 belongs to class 1 with a degree of belief 0.6. We believe object 2 also belongs to class 1 with a degree of belief 0.5, and we believe object 3 belongs to class 2 with a degree of belief 0.7. So here M, F, and so the extension of the extent to M superscript F is a combined mass function, okay, in F, okay. So here I have a notation, 1, 1, 2 means that object 1 is assigned to cluster 1, object 2 cluster 1, object 3 to cluster 2, okay. So what is the mass function of that? So here you multiply, you have this is object 1 belongs to cluster 1, so you multiply the 0.6, okay, with 0.5, okay, because here you take the mass m2 of omega 1 and multiply by 0.7. Okay. So this, if you intersect the set of labeling relations such that object 1 is assigned to cluster 1 with a set of labeling functions such that object 2 is assigned to cluster 1, and the set of labeling functions such that object 3 is assigned to cluster 2, you have only one relation, which is this one. Only one labeling function. Okay? And so the mass here is a product of these three numbers. Okay? And then you can take here all the way to multiply the three numbers. So for example, here, if you intersect, okay, you consider this one and this one and this one. Okay? So you consider the set of labeling functions such that cluster 1 has object 1 has label 1, object 2 has label 1, and object 3 has either label 1 or label 2. Okay? This I denote like this. Okay? And the mass is 0.6 times 0.5 times 0.3. Okay? And you continue like that. For instance, here you have you multiply this, you consider this one, and this one. So the set of labeling functions is the set of functions so that object 1 is mapped to cluster 1, object 2 is mapped to either cluster 1 or cluster 2, object 3 is mapped to cluster 2, so this is this focal set. Okay, this notation for a set of labeling functions, and the mass will be the product of this times this one times this one, which is 0.21. Okay, so we get eight focal sets like this. A mass function on F with 8 focal sets. Now here we have 3 objects and 2 groups, so there are only 4 partitions into at most 2 groups. Okay, so either a partition with only one group, okay, all objects are in the same group, or you have O1 alone and O2 O3, or O2 is alone or O3 is alone. Okay. So, and now we can define this mapping. So here this corresponds to 1, 1, 2 corresponds to P3, okay, because 1 and 2 are together, object 2 is alone, okay. And okay, and we can like this for each set of labeling functions, give the set of corresponding set of partition. For instance, here this corresponds to object 1 and 2 are in the same group. Okay, and object 3 may either also be in the same group as the other 2, or maybe alone. So the corresponding partitions are either P0 or P3. Okay, when object 3 is alone. Okay. You can take here another example. For instance, this relation. So object 1 and 2 are object. Okay, so here object 2 is assigned to cluster 2. Okay, object 1 and 3, they can be either in cluster 1 or cluster 2. Okay, so actually it's not okay. Yeah. So we can have either 1, 1, 1, okay, which corresponds to B0. Or we can have 1, 2, we can have 2, 1, 1, okay? So this corresponds to P1, okay? Or we can have 1, 1, 2, okay? And this corresponds to 3 being alone, okay? So all the 4 partitions are possible. So here, it's the whole set of partitions, P sub 2, okay? So you see, you continue like that. So to each set of labeling functions, you can assign a partition and you can sum up the masses, okay? For example, you have here P2 is here, 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 and here. So you sum up the masses assigned to these 4 focal sets and you get 0.35. So you get a mass function on the set of partitions. Okay, another notion is that of pairwise mass functions derived from a Credal partition. Assume you have a Credal partition. Here, we'll use it extensively later in the slide. So this is an important point here. So we start with the Credal partition. We consider 2 objects, OI and OJ. And we ask the question, do they belong to the same group or not? So here we define the frame theta ij with 2 elements, Sij, meaning they belong to the same group, or not Sij, meaning they belong to different groups. So now I consider omega times omega, the Cartesian product of, so this is a set of all pairs of a cluster for object 1 and a cluster for object 2. So you see here, if I have 4 clusters, for example, omega square, omega cross omega, the Cartesian product, has 16 elements. I consider this set, the set here corresponding to the diagonal, okay? So it has omega 1 and omega 1, omega 2 and omega 2, and so on, okay? So you see that actually this omega square is a refinement of theta ij, okay? And because it is because it is the same thing to say that Sij is true and to say that the pair of clusters for object I and j are on this diagonal. It's the same to say that object I and j are in the same group, or to say that either they both belong to cluster 1 or they both belong to cluster 2, and so on, okay? And it is the same to say that object I and j are not in the same cluster, and to say that we are somewhere out of the diagonal, okay? So theta ij here is a concerning of omega squared. So given now 2 mass functions mi and mj on omega, we can compute a pairwise mass function mij as follows. So we vacuously extend mi and mj to omega squared. And we have seen that the operation, when you have a mass function on a concerning, you can extend that on the refinement. Okay, when we combine the extended mass functions by the Dempster's rule, okay, but without normalization, because here we use a version of Dempster-Shafer theory where we allow mass to be assigned to the empty set, and then we compute the restriction of the combined mass function to theta. So, okay, this is just a way to compute. If you have some beliefs about the group of object I, and you have some belief about the group of object J, you compute your beliefs about whether the 2 objects belong to the same group or not. Okay, and this is technically how it is done, and this is the resulting mass function. So I will come back several times to this slide because it will be used by some clustering algorithms I will describe later. You see here we get this very interesting equation here, and that the plausibility that the objects belong to the same group is 1 minus the degree of conflict between the two mass functions. This is what I mentioned yesterday, and I said that this is true, but here we see where it comes from. Okay, so the plausibility that two objects belong to the same group is 1 minus the degree of conflict between the mass functions mi and mj. Okay, but we can compute these four masses. Okay. You see that here, if the mi and mj are normalized, meaning that the assign is 0 mass to the empty set, here the mass on the empty set will also be 0. Okay. And here we'll just have the belief that they don't belong to the same group will be exactly equal to kappa ij. Okay, so this is an example. Here I have 3 objects with that Credal partition, the mass function, and here we compute the 3 pairwise mass functions. Okay, so you see that we rather believe that object 1 and 2 belong to the same group. Okay, because we believe that object 1 belongs to cluster 1 and object 2 belongs also to cluster 1. Okay, so we have more mass assigned to Sij than to not Sij. And for objects 1 and 3, okay, for object 1 and 3, so we believe to some extent that object 1 belongs to cluster 1 and object 3 belongs to cluster 2. So we should believe that they do not belong to the same cluster. And indeed, we have more mass here assigned to not Sij. Okay, and similarly for 2 and 3. So I sometimes call this the set of all these pairwise mass functions, the relational representation of the Credal partition. Okay, you get a mass function for each pair of objects. Okay? And some of the algorithms I will describe later use these results. Okay, so here now I will describe some evidential clustering algorithms. There's a lot, so I'm not sure I can do everything, but I will see which point I can go. So in the following, I will see an algorithm for finding the most plausible partition given a belief function of the set of partitions obtained as the orthogonal sum of pairwise mass functions. So it's the first model I described previously. Okay? And we'll see a heuristic algorithm that finds actually some local maximum of the plausibility over the partitions. And then we'll see 4 algorithms for constructing Credal partitions. And okay, well, see, I may not have time to describe everything in detail. We'll see how fast we go. So all these 5 algorithms are implemented in an R package, EVCLUS, which is available online. So the first algorithm, I call it EK-NNclus. So it is an example of a decision-directed clustering algorithm. Okay, what is this? So it's a whole approach to design clustering algorithm, starting from a classifier. Assume you have a classifier. Okay, you can first randomly initialize the classifier and use it to label the samples. Okay, so now you have a label samples. Then you retrain your classifier, okay, and then you do it again. Now with an updated classifier, you classify the objects, okay, and you do it again and again until you converge to a partition. So the C-means algorithms, C-means or K-means algorithms, I don't know if you know this algorithm or not. We'll see a refined version later. It belongs to this principle. Here the classifier is the nearest prototype classifier. Okay, so first you initialize the prototypes in any way, then you classify each object according to the nearest prototype, and then you recompute the prototypes as the center of mass of each cluster, and you iterate, and you can show that it converges to a stable partition. So here we are going to use the same principle with some classifier based on belief functions, which is called the evidential EK-NNclus. classifier or evidential KNN rule as a base classifier. Okay, so I will quickly present this classifier. Maybe it will be presented tomorrow. I think it's tomorrow that Professor Junga Liu will give a lecture on evidential classification. So I think he will probably mention this, but we'll summarize it briefly here. And so this corresponding clustering algorithm, which is the application of this decision-directed approach with a evidential KNN rule as a base classifier, I call it EK-NNclus. So we start with a symmetric matrix of distances or the similarities between the n objects. Okay. So either this was computed, either you had attributes and you just computed some distance, like the Euclidean distance, or sometimes you may just have that matrix to begin with. For instance, if you analyze, if your objects are some agents in a social network, for example, okay, you can say that two agents are all the more similar that they exchange more messages, for example. Okay, so it's a measure of similarity. Okay, so you may start with this data set. You don't describe the agent by attributes, but you have some measure of how close to any or how close to any two objects are. So we fix some number k, and we compute the k nearest neighbors of each object I. So for each object I, we search for the k objects which are the closest, okay, to I, and we denote the corresponding set of indices as n sub k of I. Then we transform the distances by some function phi, which is a decreasing mapping from R plus a set of positive real numbers to the interval 0, 1. Okay, I show later the form that this function phi can take. So it means it's a decreasing mapping. So actually the alpha ij can be seen as similarities, okay, between 0 and 1. Okay, how to fix k? If computing time is not an issue, k can be chosen very large, even equal to n minus 1. Okay, so in that case, we consider all the objects. Okay, to initialize the algorithm, the objects are labeled randomly. You assign random labels. So you don't, but usually you don't know the number of clusters you're looking for. So you can just initially say that each object is in its own cluster. Initially, there are as many clusters as objects. Okay. But of course, if n is very large, we can give C a large value. For example, if you have 10,000 objects, you can say start with 1,000 clusters and randomly assign the clusters. So we'll denote cluster membership by binary variable yik. Yik was 1 means that object I belongs to cluster K, and yik is equal to 0 otherwise. Okay, so this is notation to indicate at a given time the label of each object. Okay, so then an iteration, so it's an iterative algorithm. An iteration of the algorithm consists in updating the object labels in some random order. So you pick some random order, and you start to update the labels of these objects. How you do this? For any object I, you assume that the evidence from its neighbor, let's say OJ, is represented by a mass function like this. Okay, so if J, the neighbor OJ, belongs to cluster K, you put some mass on omega K. And here the mass will be alpha ij. Okay. So you see, the larger the distance, the larger the distance between OI and OJ, the smaller alpha ij. Because if the object I and J are very far, the evidence from object J is weak. Okay, so the mass here should be small. Okay, so we have k mass, if we consider k neighbors, we have k mass functions like this. They are simple mass functions, but yesterday defined simple mass functions. We combine them by Dempster's rule, so it's very computationally efficient to combine simple mass functions. And then we assign object I to the cluster with the highest plausibility. So you see this way of defining mass functions and combining them, this is called the evidential k-nearest neighbor classifier. Maybe Professor Liu tomorrow will describe again this method. Okay, this is an algorithm I published in 1995, a very long time ago, but it's been very popular. It's been quite used many times. And so if the label of at least one object has changed during the last iteration, then we continue. We randomly reorder the objects and we start a new iteration. Otherwise, if no object label has been changed, now the partition is stable, so we stop. So here is an example of what we get with an example, very small, simple example of data set. So here we have found a partition into 3 clusters. Okay, so we didn't specify the number of clusters. Okay, the algorithm converged by itself to a partition into 3 clusters. And here on the right, the symbols, the size of the symbols are proportional to the mass on omega. So for this algorithm, it's not the same as for other algorithms I will describe later. For this algorithm, the outliers have a large mass assigned to omega. Okay, so does this algorithm converge? Does it stop? So actually, we can show that if the number of neighbors k is n-1, okay, so we take all the points, then each update of a class label during an iteration of this algorithm strictly decreases some energy function defined like this. Okay? And because there is only a finite number of partitions, finally the algorithm converges to a stable partition in a finite number of iterations. So this first theorem tells us that the algorithm converges to a stable partition. In practice, we can still observe convergence if k is even much larger than n-1, although the rigorous proof was given only for the case k equal to n-1. Okay, so maybe this is also true for k less, the smaller value of k, but I never found a case where it didn't converge, even for a small k. And now we have this equality that the plausibility of the partition P encoded by the class labels in the orthogonal sum of pairwise mass function model, which we have seen before. Okay, so in this model, actually this function log of P with all the beta ij equal to 0, so we don't have this term, but we have only this term. This is the same up to some sign as this is minus our energy function plus some constant. Okay, so when the algorithm minimizes the energy, it maximizes the plausibility of the partition. So this algorithm can be seen as a greedy search. This is a greedy search algorithm that finds a local maximum of the plausibility contour function in the space of all partitions in the data set. Okay, you can interpret this algorithm as finding an approximation, okay, of the most plausible partition. Of course, as any optimization algorithm, it finds only a local optimum. Okay. So this is an example of how it can work. So the function phi can be defined like this, just a decreasing exponential. So here you have some parameter gamma to fix. In practice, it can be fixed as the inverse of the Q quantile of the set of distances to the k nearest neighbors. It's a scale parameter. Okay, so you just fix it based on you see the distribution of distances of the k-nearest neighbors, and you take the some quantile. So here I will show the results of the algorithm on two-dimensional data sets, two-dimensional data sets with 20, 35, and 50 clusters. Okay, so I take data set with a very large number of clusters, and we don't know the number of clusters. Okay, so the algorithm will discover by itself the number of clusters. Okay, so we used 150 neighbors for first data set and 200 neighbors for the other data set. A rule of thumb is to choose a number of neighbors of the order of 2 to 3 times the square root of the number of objects. So we can initialize with our two initialization methods. Either we initialize the algorithm with as many clusters as objects, but it can be slow at the beginning, okay? Or we chose 1,000 randomly initialized clusters. So I run the algorithm 10 times, and okay, this is these are these examples of these data sets. You see, these are maybe A1 and A2. You see, they have a very large number of clusters. Okay, so here we want to discover automatically the number of clusters. So here we see for each data set the result. So A1 has 20 clusters, okay, and EK-NNclus initialized with as many clusters as objects always found 20 clusters. Okay, so it always found the correct answer. And also, if we initialize only with 1,000 clusters, it still found all the time the 20. And these are 3 alternative methods. This is a non-parametric algorithm for searching the mode of the density. It found 17 clusters. And the model-based approach with a mixture of Gaussians, it found 24 clusters. Okay, by the AIC, for example, you have a model and you maximize AIC. So this algorithm was better at finding the number of clusters. So A2 is 35, and we find always in the 10 runs, we always find 35. And this one has 50, and here we found 49 clusters. This may be the standard deviations. So it's maybe 49, maybe 50. And this is the computing time. This must be in seconds. And the computing time is also less than in the non-parametric or model-based. Okay, so same order as a non-parametric in the model-based approach. Okay, so this is one approach where we have an algorithm that is a heuristic search algorithm for finding an approximation to the most plausible partition. And you get also, as a byproduct, you get a Credal partition, a different kind as with the other algorithm, because the outliers, the mass functions are normalized, and the outliers correspond to the large mass given to omega. Okay, next, we'll see 4 other algorithms that this time find directly a Credal partition. So the problem here is to generate a Credal partition. Okay, and here we assume that we have, okay, so this method I'm going to describe is called the evidential C-means. Okay, so it is an algorithm in the same family as the C-means, the hard C-means algorithm, or the fuzzy C-means. Okay, there is also a possibilistic C-means. Okay, so this is evidential C-means. Okay, so it's a C-means-like algorithm that finds a Credal partition. So here we assume that we have attribute data. Each object is described by a vector of attributes. And, okay, as the C-means or fuzzy C-means algorithm, it's a cyclic coordinate descent algorithm. It means it will be based on fixing some prototypes. And for this fixed prototype, you optimize the Credal partition, okay? And then you fix the Credal partition, you optimize the prototypes, okay? And so and you can show that by doing that, you minimize some cost function. Okay, here I recall the fuzzy C-means. And maybe most of you maybe know the fuzzy C-means if you have worked on clustering or machine learning. So in the fuzzy C-means, so remember that it's a fuzzy clustering algorithm. So we want to find for each object I, the numbers uik. Uik is the degree of membership of object I to cluster K. Okay. So we do this by minimizing this cost or loss function, okay, which is the sum over the objects and or the sum over the groups of uik to the beta times dik squared, where dik squared is the distance between object I and some prototype of cluster K. Okay, so we have, if we have say groups, here we have to fix the number of groups in advance. For each group we have a prototype vk, okay, and we try to minimize this. So it means that when the dik is large, if object I is far from the prototype cluster K, we should have uik that should be small, the degree of membership, because we try to minimize the sum of these products. So when the distance of a prototype K is large, the degree of membership of the corresponding cluster should be small. Okay, and it can be shown that this criterion can be minimized by this alternate optimization algorithm. So here in the first step, at each iteration, there are two steps. In the first step, we update the prototypes. Okay, the prototype adjusts centers of mass of the xi's with masses defined as by uik to the beta. Okay, and then we fix the prototypes and we update the membership degrees. Okay, but it can be shown that each time you do this and this, you decrease that function. Okay, so you converge to some local minimum. So in ECM, we also represent each cluster by a prototype. Okay? For example, here we have three clusters. We have three prototypes, V1, V2, V3. But now we also represent each non-empty set of clusters also by a prototype, which is defined at the center of mass of the prototypes for the clusters in that set. For instance, here we have the prototype for cluster 1, prototype for cluster 2, and here this is the prototype for the union of cluster 1, cluster 2. Okay. So if some attribute vector is close to here this V2 bar, we'll give a large mass to the union of cluster 1 and cluster 2, okay, because it is like halfway between the two clusters. So here the idea is that for any non-empty set of clusters Aj, the mass Mi of Aj should be high if Xi is close to the prototype representing that set of clusters Aj. And the distance to the empty set is defined as some fixed value. Okay, and we define this loss function. So here, curly F is a set of non-empty focal sets that we consider. Okay, because of course in evidential clustering, if you have, let's say, 10 clusters or 20 clusters, you may not want to have 2 to the 10 or 2 to the 20 focal sets. Okay, so sometimes you reduce the focal sets. Okay, so here we have small f, lowercase f, distinct non-empty focal set that we consider. For example, all the singletons and the pairs, for example. Okay, and sometimes you can put also omega. So we minimize this subject to the constraints that the masses for each of them sum to 1. Okay, so you see that here we want Mij. So Mij is a mass assigned to the focal set Aj. It is multiplied by Dij, which is the distance between the vector of object I and the prototype corresponding to the set Aj. So we want this to be small when this distance is large. And here we have the mass on the empty set, which is multiplied by a fixed parameter delta, which we interpret as a distance to the empty set. So this algorithm has three parameters. Alpha controls the specificity of mass functions, because here you see, we multiply also this. Here we have the cardinality of aj to the alpha. Okay, so here the goal here is to reduce the mass assigned to big focal sets. Okay, we want the mass function to be as specific as possible, and so you can control the specificity of the mass functions by this parameter alpha. Beta control the hardness of the Credal partition, like in fuzzy clustering. I didn't comment on beta for in fuzzy clustering before. So basically, okay, the default is 2. If you, I think if you increase beta, the mass is more spread across the different, is more evenly spread across the different focal sets. Okay, if beta is smaller, it is more concentrated on a small number of focal sets. And delta controls the proportion of data considered as outliers. And so here we have the algorithm, and we update the Credal partition with the prototypes fixed. And then in the next step, we update the prototypes. Okay. Updating the prototypes here is more complicated than in fuzzy clustering. You have to solve a system of linear equations. Okay, but it can be done. Okay, this is an example here with the butterfly data set I showed before. So you see here the what is this? It is green, this one? Yellow, green? Green, okay. So you have the green curve here. It is a mass given to cluster 1. So you see that, for example, object 3 here as a mass assigned to cluster 1 because it's the center of the cluster. Now in blue, you have the mass assigned to cluster 2 for the different objects. Okay, so you see that object 9 has a mass almost equal to 1 for cluster 2. Now this one, it's cyan, or okay, this one in the middle is a mass assigned to cluster 1 or cluster 2. So object 6 gets a large mass to the cluster, either cluster 1 or cluster 2, and the red is the mass on the empty set. So object 12 has large mass on the empty set. Okay, this is a Thierry data set. Here we see this is what we get with a more realistic, let's say, data set. So there are 4 clusters, and see here I plot the lower and upper approximation of the clusters. Okay, so the lower approximation are the set of objects that surely belong to a cluster. Okay, actually they are the set of objects for which a singleton cluster has the largest mass. Okay, and then you have for each cluster you have a larger set of objects that possibly belong to the cluster. But this is this is just for representation purposes, and this is a rough partition derived from the Credal partition. But actually, the information we have is more detailed than that. Okay, in some cases, we may have some prior knowledge about the group membership of the clusters. Okay, this is can be called semi-supervised clustering. Okay, we want to find a group, but an expert, or by using some indirect method, you can get some prior information. And one very convenient way to elicit this kind of information is to define what we call must-link constraints and cannot-link constraints. So we take a pair of objects, okay, and so if the expert tells us that these 2 objects are in the same group, okay, then this is a must-link constraint. And if we know that 2 objects do not belong to the same group, we call this a cannot-link constraint. So we assume that some expert, or we're using some indirect method, for small, usually a few pairs of objects, you can have this kind of information. So how to exploit this information? So this is done in the CECM, like constrained ECM algorithm. So you just add to the loss function of the ECM algorithm some term here like this. Okay, so what does that mean? So here you try to minimize this. Okay, so you try to for if X object I and J are linked by a must-link constraint. Okay, so the expert tells us that they belong to the same group. We want the plausibility that they don't belong to the same group to be small. Okay. And the expert told us that I and J do not belong to the same group. It's a cannot link constraint. When we want the plausibility that they do belong to the same group to be small. Okay. So by this term here, we try to enforce, okay, having for the Credal partition to be consistent with the constraints, okay, given by the expert. And how to compute these? That we go back to these pairwise. Sorry. Oops. We go back, and we have seen how to compute the plausibility that any two objects belong or do not belong to the same group. Okay, so we can use this formula. This is a plausibility they belong to the same group. The plausibility they do not belong to the same group is the sum of this mass and this mass. Okay, so we know how we have this formula, and we can do the computation. Okay, and actually minimizing this criterion is a quadratic programming problem, so it can be done relatively efficiently. Okay, we can also, but sometimes the constraints are given in advance, but sometimes we can have some active learning strategy, okay, where we choose the pairs. We choose the pairs of objects that will give us, we think they will give us more useful information. Okay, so one strategy is to select pairs of objects. So starting with some initial Credal partition, now you want to improve that partition. You take a pair of objects such that the first object is classified with high uncertainty. Okay, so we are very uncertain about this object, and then you pair it with an object classified with a high certainty. For example, it is close to a cluster center. Okay? So you take one object for which you're pretty sure which group it belongs to, and an object for which you're quite unsure. Okay, so knowing whether these two objects are in the same class or not is very useful information. So here you see, for example, so here this is the number of for two data sets, the number of constraints, and here you have the RAND index, which is a measure of the quality of the partition as compared to a ground truth partition. Okay, and you see, so here you have the evolution of the RAND index with the number of constraints. So the more constraints, the better the partition. The closer is the partition to the true partition. Okay, but this is without active learning, and this is with active learning. You see that your performance increases faster. Okay, so this active learning is a quite good strategy. Okay, there has been quite a few variants of that algorithm. There is a relational evidential C-means that can handle distance data instead of attributes. There is a spatial evidential C-means algorithm for image segmentation, because in image segmentation, the objects are the pixels. Okay, and you must have some constraints. You expect two neighboring pixels to be in the same group. Okay, so you can add in the cost function of ECM, you can add some constraints that forces neighboring pixels to belong to the same group. Okay. And this is another. There was another variant where you also adapt the distance metric. Okay, and this is another clustering algorithm which is somewhat similar to ECM. It was proposed by Professor Junga Liu, but with a different definition of the distance between a vector and metacluster. Metacluster is a cluster representing a set, or is a prototype. Metacluster is a set of clusters. So it's a variant which sometimes work better, sometimes worse. Okay, so the next algorithm is, I call it EVCLUS, like evidential clustering, and it's based on different principles. In a way, it's more, maybe more, its application is more general, it's more powerful than the previous one. And actually, I like it better than the previous one. So here we start with a dissimilarity matrix, a matrix of distances or weaker forms of distances between objects. We don't assume that we have attributes. If we do have attributes, we can always compute distances between the attributes, okay? But it's not required. So based only on the distances or dissimilarities, how can we build a reasonable Credal partition? So we need a model that relates cluster membership to dissimilarities. And we will use this following principle. We assume that the more similar are two objects, the more plausible it is that they belong to the same group, okay? Because what is a group that we search in clustering is a group of objects which are close, okay, to each other, okay? So the more similar are two objects, the more plausible it is that they belong to the same group. So how can we formalize this idea? So let Mi, Mj be mass functions about two objects Oi and J. We have seen before that the plausibility that object I and J belong to the same group is 1 minus the degree of conflict between Mi and Mj. So we want to find a Credal partition such that larger degrees of conflict between any two mass functions correspond to larger dissimilarities. The smaller the distance, the less conflict, and the larger the distance, the more conflict. So we can define a cos function like this, where we minimize the sum over all pairs of objects of the degree of conflict kappa ij between mass Mi and Mj, and some transformation of the distance dij. Phi here is a mapping that rescales basically the distance between 0 and 1, because the degree of conflict is between 0 and 1. We can use a transformation like this. Okay, this scale parameter here can be determined by some heuristics. I will not comment on this, but this is basically the idea. Okay? We search a Credal partition such that if you take two mass functions Mi and J, you compute the degree of conflict. It is close, okay, to the transform distance between the objects. Okay, so larger objects more farther away have more conflict between their mass functions, and if they are close, they should have small conflict because they belong to the same class. Okay, so I will skip this and show the result. Okay, so this algorithm that minimizes the criterion I've just shown is called EVCLUS. So this is a result we get on the butterfly data. So we see as expected that, for example, object 6 has a large mass on omega, object 3 and 9 has a large mass on class 1 and class 2, object 12 has a large mass on the empty set. Okay. Okay, here for this data we have this. So here I have to comment that the idea of this algorithm comes from multidimensional scaling. What is multidimensional scaling? You have distances and you're trying to find vectors such that the Euclidean distances between the vectors match the dissimilarities. Okay? So you start with a matrix of dissimilarities, and you try to find a representation of the data in some Euclidean space such that the Euclidean distance between any two vectors match the dissimilarity. So here the same idea, except that instead of searching for vectors in the Euclidean space, we search for mass functions. And instead of the Euclidean distance, we have a degree of conflict. And so this is a type of graph called in multidimensional scaling a Shepard diagram. It shows here the degree of conflict versus the transformed dissimilarities. So you see here we can check we can check with this kind of graph the matching, and how well we have matched the dissimilarities with the degrees of conflict. Okay? So you see here, points which are farther away have a large conflict between their mass functions, and points which are close together, they have a small conflict. Okay, and here this is what we get with a 4-class data set of 2,000 objects. So here I show for each cluster, we show the lower approximation and the upper approximation, and the circled points are the outliers. So the outliers here have the largest mass is assigned to the empty set. Okay. So the algorithm can detect the clusters. So we sum with some imprecision. Okay, we can represent the uncertainty in the clustering. For example, a point here, okay, may belong to that blue cluster. Okay, but it may also belong to, for instance, this black cluster. Okay, so these points here are ambiguous. Okay, and we can also detect the outliers. Okay, here this is an example with a data set about proteins. We have 213 protein sequences, and we have only the dissimilarities. Okay? And the dissimilarities are not metric, they are not distances. So many clustering algorithms, like relational fuzzy semis or that, fail with this kind of data. They don't converge because the dissimilarities are not Euclidean distances. Okay? But here we get a very good partition of the data. Okay, and here, because here we know the ground truth, there are actually 4 classes of molecules, and we find the true partition with only 2 errors. Okay, so and this was a very challenging data set. Most clustering algorithms fail on this data because, once again, the dissimilarities are not Euclidean distances. Okay, so this method is conceptually simple, easy to interpret. We can understand, I think, quite well the criterion that we optimize. It can handle non-metric dissimilarity data, even expressed on an ordinal scale. And it was shown to perform quite well as compared to relational clustering techniques on a number of data sets. But it also has some limits. One is that we have to store the whole dissimilarity matrix. Okay? So because we work with the matrix of dissimilarities between the objects. So if we have, for example, 10,000 objects, we have a matrix of size 10,000 times 10,000. Okay. If we have 1 million objects, that's a matrix of 1 million. We cannot store this. Okay. So in practice, because of this, we cannot handle data sets larger than a few thousands of objects, for example. And also each computation of this is a gradient-based algorithm to minimize the cost function. And its complexity, as you see, is of the order. So here F is the number of focal sets. Okay. And in the worst case, the number of focal sets is 2 to C, to the C, where C is the number of clusters. So it can be quite costly. So there are 2 ways we can improve the algorithm to make it work on large data sets. And this is something, you see, if you apply belief function with a brute force approach, of course you cannot handle very, it's like in the graphical models, if you want to extend the mass function, the joint on the whole space, of course you cannot do it, but you need to be smart and try to find clever ways either to do the calculation in a smart way, as you do with the BBS, or to do some suitable approximations, or to try to find some simpler models. So here there are 2 improvements. We don't need to consider all the dissimilarities. This is a key point. And another improvement is to carefully select the focal sets. So I will show you this. Yeah. So actually, you have a dissimilarity matrix, okay? But there is some redundancy in there. Because, for example, if 2 objects, say O1 and O2, are very similar, then any object O3 that is similar to O1 is usually also O3 dissimilar from O1 is usually also dissimilar from O2. Okay? You have 2 objects which are close to each other. If you have an object O3 which is far from O1, it is also far from O2. Okay, so this is this kind of redundancy that we can exploit by not considering all the dissimilarities. So here we can proceed like this. We can fix some number k, and for each object I, we take only k dissimilarities to k objects. Okay. So if you have this dissimilarity matrix. Okay. So here you take some object I. So here you have on this row the dissimilarities to the n objects. Here you do n times n. But instead of taking these n dissimilarities, we randomly sample k values on this row. Okay. For the next year, say I prime, we sample also randomly different. So we randomly sample in the matrix. And so this is a modification of the criterion. And now the calculating the cost function requires only a number of operations proportional to number of objects times k instead of n squared. Okay, so it's now proportional to n rather than n squared. So here we have for some simulated data with 10,000 objects. So we have 10,000 objects. Here we see the adjusted RAND index. It's another measure of the quality of a partition as compared to the ground truth as a function of k. And you see that with as few as maybe 200, okay, k as few as 200, okay, we can get a partition as good as if we take all the whole matrix. Okay, so you have a matrix of 10,000 times 10,000, but in each row we just sample only 200 values among the 10,000, and the algorithm still works. Okay, and here this is computing time. The computation is also much faster like this. So this is really a drastic improvement. Here we have some dissimilarity data. We have 2,000 handwritten digits in 10 classes, and we only have the distances, okay, between the digits. It was computed by deformable template matching. So we use EVCLUS with a c equal to 10, different values of k, and here this is what we got. Once again, we see that with only k, maybe 100 or 200 is enough, okay, and the computation time is much smaller. Okay, the other thing is how to select the focal sets. Okay, because for example, if you have 10 clusters, you have a maximum of 2 to the 10 focal sets. Okay, and that increases exponentially with the number of clusters. Okay, so we can, for example, decide to allocate masses only to pairs of clusters. For example, to all singletons and pairs. But still, the number of focal sets is still proportional to c squared. This is manageable for moderate value of c, but impractical for larger c. So here the idea is to assign masses only to pairs of contiguous clusters. And we will, okay, so so if each cluster has at most q neighbors, then the number of focal sets will be proportional to c. It will be c plus or c times q, only proportional to c. So you see here, there's an example of a data set. It's one of the data set that it was used also to evaluate the previous algorithm. And it has 15 clusters. And you see that, okay, it makes sense to assign some mass to the union of these two clusters. But for this one and this one, it's useless. So we try to identify the pairs of clusters which are close to each other. And so the method is this. First, we run a clustering algorithm with focal sets of cardinality 0, 1, and maybe c. Okay. You can even use the hard clustering or fuzzy clustering algorithm. then you obtain some Credal partition, okay, but the masses are only on the singletons. Then you compare this, you try to compute the similarity between each pair of clusters, and it can be done like this, okay? Two clusters are similar if for all the objects, okay, the plausibilities of belonging to the two clusters are high, okay? So this is a measure of the similarity between two clusters. And then we determine the set of pairs of clusters that are mutual k nearest neighbors, okay? It means that cluster K, for example, is one of the k nearest neighbors of cluster, or say cluster J is one of the k nearest neighbors of cluster L, and conversely, cluster L is among the k nearest neighbors of cluster K. Okay, this is called the pairs of mutual k nearest neighbors. And then you run again the clustering algorithm, like ECM or EVCLUS, starting from the previous Credal partition, but adding as focal sets the pairs of mutual Q nearest neighbors. So here we see that we find for Q equal 1, we have 4 pairs of mutual 1 nearest neighbor. Okay. So these are the clusters that really overlap. Okay. And then we'll add these 4 pairs as a focal set and run again EVCLUS, for example. Okay. If we take Q equal 2, we have a little bit more pairs. And so here, this is the initial Credal partition M0. Okay, so we don't have any mass assigned to the pairs of clusters. And here, this is after we the next step, after we run again, adding these pairs. And here I represent the ambiguous objects. Okay, so now we can identify the ambiguous objects, okay, that are in overlapping regions. Okay, so this solves the problem of the exponential increase of focal set with the number of clusters. You can carefully choose the focal sets. Okay. And so you can use evidential clustering even if you have a very large number of clusters. And here you have 15 clusters, you can have even more. Okay, so now the next algorithm is a version of the previous one, but that has some improvement in some way. Okay, if you compare ECM and EVCLUS, you see that EVCLUS does not build a compact representation of the clusters as a collection of prototypes. Okay, it learns directly the Credal partition. So the number, if each mass function has f focal sets, the number of free parameters in the model is n times f minus 1 because the sum of the masses is 1. Okay, so you have as many non-parametric. Okay, so if you have n objects, like 10,000 objects, and 10 focal sets, you have 90,000 parameters to optimize. Okay, in the Credal partition. Okay. So this characteristic makes EVCLUS impractical for clustering very large number of data sets because the number of parameters increases linearly with the number of objects. Also, if you have learned an evidential partition from a given data set, you cannot extrapolate to new data. You would like to be able, after you have found the evidential partition, Credal partition, you would like to be able to label new objects. And with EVCLUS, you have to rerun again the whole optimization if you have new objects. So NN-EVCLUS is a neural network version of EVCLUS that addresses these issues. So the data here, we assume the data consists of 2 things: a dissimilarity matrix, like with EVCLUS, and also a collection of attribute vectors. We assume that we have these 2 things. So most of the time we have attribute vectors, okay, and we can compute distances by, for example, Euclidean distances. Okay, so sometimes we start with the vectors, attribute vectors, and we can compute the distance matrix. Sometimes we have only the distance matrix. Okay, then we can still compute attribute vectors using, for instance, principal component analysis of this distance matrix, okay? Or multidimensional scaling, or there are many methods in machine learning to embed, okay, some dissimilarity data into some space, okay? But this case is less common than the previous case. In many applications, you do have attributes. So you have attribute vectors, you can compute distances between the attribute vectors. So here we compute a vector represent, okay, so we assume that M bold denotes a vector with the masses, okay, for one object, the vector of masses, okay? This is a vector representation of a mass function. We have a model where this is the output of a multi-layer neural network, okay? So we define a neural network. We have a neural network, okay, where an input layer here. So here the input is vector x. Then you have a number of hidden layers. Oh. And here you have the output layer. The output layer is a vector of masses, mass function. Okay. So typically we'll have a softmax. Those of you who know a little bit about neural networks, they should understand what I'm speaking about. You have a softmax layer so that you have the output sum to 1. Okay. So here what comes out is a mass function. Okay. So we want to learn this neural network. It can be deep or shallow, it doesn't matter. Okay. So M depends on X, and theta is a vector of weights in the neural network. Okay. So this time we want to, so by doing this, we compile the data set into a smaller number of parameters. So here we also we know that this kind of neural network, it will not allow us to detect outliers, okay? Because what we have outside the data set can be anything, okay? So to keep this property of EVCLUS to identify outliers by the mass of the empty set being high, we also use a one-class support vector machine. Okay. A one-class support vector machine is a kernel method that allows for novelty detection. So it will, if we have some data, it will give us as output a function that is high. I think this is the direction. It will give us an output a version that is high in the region of high data density and low outside. Okay, or I don't remember if it's the other way around. Okay, but you can just change the sign, it doesn't matter. And so it will give us some function like this. Okay, and by defining a threshold, you get some region here that contains the data. Okay, it's close to the convex hull of the data. Something like that. And so when you are outside this region, you probably you have an outlier. Okay, so here we define the complete mass function M star. It is a weighted sum of the mass function M for the neural network plus some mass M empty set with only the empty set is only focal set. And here gamma depends on the output of the one class SVM. Okay, so when the SVM detects that we are far from the data, the mass on the empty set becomes large. It doesn't matter exactly what are the formula, you will have the slides, and of course. So, okay, so here the whole model, you have the vector x, you present it to some neural network, it gives you some mass function m. Then here from the one class SVM, you compute that gamma coefficient, and then you get the M star, which is a combination of M and M empty set. Okay. Then how will you train this network? You A training instance is a pair xi, xj, a pair of feature vectors. So for xi, you can compute the mass function mi star with your neural network in one class SVM. Xj gives you mj star, and you can compute the conflict, the degree of conflict between the two. And so now you train the neural network in order to minimize this loss function. We have seen that this is an F-class principle. We want the degrees of conflict to be small when the dissimilarities are small, okay? And to be large when the dissimilarities are large. Okay? So now the degree of conflict here depends on the vector of weights of the neural network. And the one class SVM is fixed, is trained separately. Okay, and so we train the network to minimize the average loss, the average over either all the pairs, but we can use the same trick as before. We don't need to take all the pairs. For each object I, we just take k other objects, okay? And we can regularize the neural network. We know, if you know about neural networks, you know that it works better if we do some regularization. Okay. And okay, so this is an example data set. Okay, so this is the output of the SVM, one class SVM. So it's actually, this is 0. So this is a kind of region that contains most of the data. And we see the contours of the function f. So it increases when you get farther from the data. And so this is a corresponding mass on the empty set. And so the mass on the empty set is 0 here, and it starts to increase when we get away from the data. Okay. And here we see the contours for the mass on cluster 1, the mass on cluster 2, 3, 4, and the pairs. Okay, cluster 1, cluster 2 is high. The mass is high when we are in the between cluster 1 and cluster 2. This is 1, 4, 2 and 3, 2 and 4, and so on. Okay, so now if we have new data, okay, we can input the attribute vector in the neural network, and the output gives us a mass function. So we can also classify new data. Okay, we can also easily exploit pairwise constraints, okay, using must link or cannot link constraints, using the same trick as we used with ECM, okay, by adding these terms in the loss function. And okay, here there is some issue, because if you assume you have a data set, and I will show you an example like this. We expect to find that in the center we have one cluster, and here around this we have another cluster. Okay, we want the algorithm to find this kind of partition. Okay, so assume that we have some constraints. Okay, so we have a must link constraint. We have to tell the algorithm that this one is the same as this one, the same group as this one. Okay, so here we say two contradictory things, because we say that when objects are far, the degree of conflict should be large, but now we say that here the degree of conflict should be 0. Okay, so how can we solve this problem? We can adapt the metric, the distance matrix. Okay, so we can change the metric in such a way that the distance between objects which we know belong to the same group is small, and the distance between the objects we know do not belong to the same group is large. Okay. And this can be done by methods like pairwise constraint component analysis, or its kernelized version. Okay, I don't have time to explain this. There is a reference in the paper I cited here. So it's a method to find a metric such that you give the algorithm pairwise constraints and the must link and cannot link constraints, and it changes the metric in such a way that objects that belong to the same group are closer, and objects that do not belong to the same group are farther. And so this is crucial to make it work actually with that. It works much better if you adapt the metric in that way. So here we have this kind of data set. So here on the left, you have must link constraints. On the right, you have cannot link constraints. Okay? So there's here the number of pairs here of constraints is much smaller than the total number of pairs. Okay, maybe 1% or something like that, or even less than 1%. Okay, and here we have the results. So here are the contours of the mass on the empty set. Okay, so when you far from the data, the mass on the empty set increases. This is a mass on cluster 1. This is a mass on cluster 2, so it's high here for data of cluster 2. And this is a mass on omega. It's high when you are in the region between cluster 1 and cluster 2. Okay, so you find the correct partition with a few pairwise constraints. Okay. So for the method to work with this kind of data of clusters, you need to have pairwise constraints, or to have some labels of some data. Okay, very quickly, I will finish with the last method. Now I spoke a lot of time already, but I will very quickly. The last method is based on a different idea. It's based on, okay, we use model-based clustering. So we use a statistical model, okay, which is a mixture model. So if you use a mixture model, like a mixture of Gaussians, okay, you can compute for each object probabilities of belonging to cluster 1, 2, and so on. Okay? We can say this is first order uncertainty. But actually you have uncertainty on these probabilities. Okay? So this is second order uncertainty. So here we would use the Credal partition notion to represent also the second order uncertainty. How are we going to achieve that? So we'll use a mixture model and the bootstrap. So we will bootstrap mixture models. Okay, I don't know who doesn't know at all what is a bootstrap. Everybody knows very well what is a bootstrap. Okay. So the idea of the bootstrap is you resample from the data. You have a data set. You create a new data set by resampling from the data. You pick some. So if you have n objects, you draw n objects with replacement from the data set. So it gives you another data set of the same size, where some objects are not present anymore, they were not picked. Some objects may be present several times. And you can do this several times, okay? And it gives you, because the rationale is that when you sample from the data, you sample from the empirical distribution. And the empirical distribution is close to the true theoretical distribution, okay, when the sample size tends to infinity. Okay, so it's a very, very clever trick. You know, that was invented by, I don't remember his name, Efron, some decades ago. And so using the bootstrap, you can compute confidence interval. Okay, so this is the idea. Okay, so here we have a mixture model. So this is the density of X. We model it by a mixture of densities within each class. So each component of the mixture corresponds to a cluster. Theta is the whole parameter vector. Theta k is the parameters for cluster k. So based on this model, we can compute the probability that object I belongs to cluster k using Bayes' rule, Bayes' formula, and it has this expression. Pi k is a proportion of cluster k in the data. So we can compute the probability that any two objects I and j belong to the same cluster by this formula. This is elementary formula of probability. Okay, so we can compute the probability that any two objects belong to the same cluster. So given a data set, we can estimate the parameter of the mixture and the corresponding maximum likelihood estimates for this pairwise probability equals to pairwise probability. So we can estimate this. And then to describe the uncertainty of these estimates, we can use a bootstrap. Okay, so we bootstrap the data. Okay, we create several replicates of the data set, and we can compute bootstrap confidence intervals on these pairwise probabilities. Okay. So, yeah, so how to do this? So, for example, you have the bootstrap percentile method. If you bootstrap, let's say 1,000 times, okay, you create 1,000 data sets. On each data set, you estimate your mixture model, you compute your pairwise probabilities, and so now you have a histogram, okay, of these pairwise probabilities, okay, and then you take the quantize, so here alpha over 2, and you leave alpha over 2 on the left, and here 1 minus alpha over 2, you leave alpha over 2 on the right. And these bounds define a confidence interval, an approximate confidence interval at level 1 minus alpha. Okay. So it means for a proportion with the probability 1 minus alpha, this interval computed that way contains a true pairwise probability. Why do I use pairwise probabilities? Because I want the method to be not to depend on the way the components are numbered. Okay, because cluster 1 for one run of the algorithm may correspond to cluster 3 in another run, but it's the same cluster. Okay? By computing the pairwise probabilities, it becomes independent on the way the clusters are numbered. Okay, and okay, so this is the algorithm, and so we choose a number of bootstrap samples. So for each bootstrap sample, we sample from the data with replacement. We estimate the parameters of the model. We compute the pairwise probabilities for each pair of objects, and then we compute the quantize to get the bounds of the confidence interval for each pair of objects. And now we remember that if we are given a normalized Credal partition, the belief and plausibility that any two objects belong to the same cluster are given by this formula, which I have used many times already. So the idea is to search for a Credal partition such that the belief plausibility intervals for each pairs of objects approximate the confidence intervals obtained by the bootstrap. And so we minimize a criterion like this, and we search for a Credal partition M such that the pairwise belief between two objects and the pairwise plausibilities approximate the bounds, respectively the bounds, the lower and upper bounds of the confidence intervals. And this problem can be solved by iteratively solving quadratic programming problems. Okay, so it can be tractable. And so for the solution to verify this, because these bounds are bounds of the confidence intervals, if we manage to find the degree of belief close to the lower bound and the degree of plausibility close to the upper bound, then we have these probabilities, these equalities here that are verified approximately. And so this corresponds to a belief function, what I call the predictive belief function. Okay, in another paper which is cited here. So it's a kind of calibration, let's say, of the belief function. We find a Credal partition such that for each pair of objects, if you compute the degree of belief that they belong to the same class, the degree of plausibility that they belong to the same class, this, say for example, if alpha is 0.05, 95% of the time, this interval contains a true probability that the object belongs to the same class. So we can give a meaning of the Credal partition in terms of this property. So here, we have some objects. So here we see object here 11 and 28. We see the distribution and the bootstrap estimates of pairwise probabilities for these two objects. So the pairwise probability is always found to be small. Okay, and here we have the the red line is okay. The red line is maybe the median, but the broken lines give you the bounds of the confidence interval. Okay, so here the confidence interval is quite small. Here you have another case, object 26 and 30. So here the bounds. Okay, they are also quite the interval is quite narrow, and so here we find that very likely the probability that they belong to the same class is close to 1. So we're pretty sure here that these two objects are in the same class. But here we have a case, I mean, these two objects, we have a case where depending on the bootstrap sample, the results vary a lot. Okay, so it means we're really not sure what is the probability that these two objects belong to the same class, and we get a very large confidence interval. Okay? So the sensitivity of the result to the variation of the data set tells us that here we have some high second order uncertainty. On the probability estimates are quite uncertain. So here we plot after training the algorithm, the degrees of belief versus the lower bounds of the confidence interval, and the degree of plausibility versus the upper bound, and we see that the approximation is quite good. The degrees of belief are actually often smaller than the lower bounds, which is good because it means our interval will be conservative. And okay, here we see the lower and upper approximation of the Credal partition. Okay. So here we use model-based clustering, statistical technique, but we use the idea of Credal partition, the additional flexibility of a Credal partition to represent second order uncertainty in the model. Okay, so I'm done. So to summarize this lecture, so quantifying clustering uncertainty using Dempster-Shafer theory implies defining belief functions on the space of all partitions. I have shown two useful workable models to represent such belief functions of these huge spaces. In particular, the Credal partition generalized not only hard partition, but also other soft clustering structures, meaning fuzzy, possibilistic, rough clustering. And I've shown several evidential clustering algorithms. Most of them generate Credal partitions. Some of these evidential clustering algorithms handle attribute data only, while few others can also handle non-metric, possibly non-metric proximity data. We can handle data sets with a large number of clusters if we carefully select the focal sets. And there is also some recent work on evaluating and comparing soft clustering algorithms, which can all be cast into the framework of evidential clustering. And here I cite a few papers on this topic. Because, for example, I mentioned the RAND index. The RAND index is a measure of how close a partition is close to a reference partition. How to generate the RAND index if you have an evidential Credal partition. Okay, so these papers try to answer this question. Okay, that's it. Thank you.